Oh. Hey, what's up, everybody? Welcome back. Another fun day of proof set theory and logic. It's Wednesday. Your exams will be back next time. Fun. Yeah, I know. Let's get into it. So today we're talking about relations. We're talking about relationships between things. Seems like a natural thing to talk about in mathematics after all. If you recall last time, really quick, we have a few different things we've seen recently. There's two basic points I guess I'll bring up. First off, for two sets, A and B, we define the product of A and B, if you recall, to be the set of all ordered pairs AB with A in A and B in B. Okay, so you got this nice old thing right here. Then for any set A, we define the power set of A to B, PA, which is the set of subsets S sets S such that S is contained in A. Okay, so we saw power sets, we saw power sets, we saw products of sets. These guys are pretty cool, they're pretty good. There's some nice ways to take sets and make things out of them. All right, we've seen other kinds of relationships you can have between sets. But there's something kind of hidden in all of this. That is, we've been writing things like the equal sign. We've been writing, these containment relationships, stuff like this. And we've really kind of glossed over what the heck all of that means. That is, we've set it up so that we have a way to talk about it. We defined what it means for sets to be equal. We say, hey, two sets are equal if they have the same elements. It makes perfect sense. It's perfectly fine. But there's this thing floating around, these like little things you put between sets. Or if we write something like, for instance, A is a much worse marker than I expected it to be. Let's see. If we write something like A is contained in B, we know what this means. We know what this subset symbol means. But all the same, these guys have been sort of flying around in the background a lot. That is, equal signs, subset signs, the things between sets, the stuff that goes between things, we've been kind of neglecting to talk about that in any way other than as like a shorthand to describe some sort of a property. But those things are objects in their own right, aren't they? The stuff you put between two sets, the stuff you put between things in mathematics, those are perfectly reasonable things to talk about. What the heck are they? Well, let's see if we can describe this very generally. So here's the idea of it. We are in section 4.1, which is all about relations. Now I'm going to keep switching markers until I find one that actually writes dark enough to be picked up on this board, hoping that there is one. All my black markers are gone. Is there one over here, actually? No, there is not. Okay, well, whatever. Here's the idea. Okay, here's a quick definition. Given two sets, A and B, a relation from A to B is a subset of A cross B. If A is equal to B, we say I'll say it this way, a relation from A to A is a relation on A. That is, we won't say from A to A, we'll just say a relation on A in the case where A and B are the same set. So what the heck does this mean? This seems too general. I'm going to try to steal this black marker. Hopefully it works. Okay. But really, it is exactly that general. So here's an idea. You've probably actually seen these before, but just not encoded in this way. Let me try to describe what I mean. A quick example. So consider the usual I'll say symbol for now, less than, like that, on the real numbers. This is a relation, or at least it defines one. In the way it is commonly used. It's a parenthesis. It's not like an L right there, just to be clear. Very bad handwriting right there. That is, we define a relation R here. Let's call this subset to be the set of ordered pairs AB such that B minus A is positive. Yeah? I'm writing it as B minus A is positive, when really I could write like B minus A greater than 0. But that would be sort of using this symbol yet again. Yeah? That is, this subset of the reals, or I guess of the product of R cross R, which people also like to write as R squared for obvious reasons. Then AB is in R if and only if A is less than B. That is, the notation A less than B is just describing which elements belong to this set of ordered pairs. Here's an easier way to think of it. If you have some way of relating things, and some things are related together and some things aren't, well then, you could just describe exactly what the relationship is by listing all of the things that are related together. Then all the things that aren't in there aren't related together. I know this sounds very broad and very general, kind of like I'm just sort of saying almost nothing, right? Like, oh, there's pairs of stuff, but really it is perfectly reasonable to talk about something in that loose of a sense, right? That is, if you want to think about any ways that any things could be related, pick seriously any way at all. Like, is someone descended from someone else, right? This describes a relation on the set of people. Like A is related to B if A is descended from B, right? Something like that, and bam, suddenly you've got Ancestry.com, right? You know, it's everywhere, these kinds of things, these basic ways of pairing things together. Any way you could possibly want to describe some things as being paired together and other things as not being paired together defines a relation. Relations are that general of a thing. They're just subsets of a Cartesian product. We give them a special name of a relation. But if you think about it, every little symbol you put between sets describes a relation. Kind of nice. Okay, kind of cool. Now, there's a lot of nice stuff we can do with relations. We can talk about lots of nice properties of them. Let's do a couple more examples. So here's another good one, another relatively straightforward one. Any equation with two variables defines the relation. Via the pairs of values that satisfy the equation when substituted for the variables. For instance, the circle x squared plus y squared equals, say, I don't know, 25. This is a circle with radius 5. Yields the relation of, well, values x and y such that x squared plus y squared equals 25. This is a subset of r cross r, right? You could look at pairs of real numbers and say, hey, if I square the first one and I add it to the second one squared, do I get 25 or do I get something else? If I get 25, I'll put it in the set. If I don't, I'll not put it in the set. Bada boom, you got a relation. Okay. Is there fundamentally really any difference between this here and what's going on with the less than sign? I guess there are differences. It's not the same thing. You don't have some sort of a symbol to mean lies on the same, or lies on a circle of radius 5. Though you could, create a symbol to mean this if you wanted. But fundamentally, in terms of what a relation encodes, there's no reason you couldn't make up a symbol for this. You could go like, hey, you could go, okay, let's write, well, let's get this stupid little string out of my way first. Oh my God. Let's see what we can do. All right, there we go. That is, you could write something like let's call it circle 5b if a squared plus b squared equals 25, right? You could make up a new little thing that you could write between two numbers to mean that they lie on a circle of radius 5. And hey, this is effectively the exact same business that goes on when you write the less than sign, yeah? It's not actually all that different. Now, this seems like a weirdly idiosyncratic thing, and I don't see any reason for us to introduce a new symbol to mean lies on a circle of radius 5 with another point. But you could do it if you wanted to. That is, like all things in mathematics, the old joke is that mathematics is all rules and no game, and philosophy is a game with no rules, right? But yeah, I mean, fundamentally, you can make up whatever rules you want. You can make up whatever symbols you feel like if it's, well, you describe what's going on nicely so the reader can follow it. Hey, you're doing math, as long as you're nice and precise with what you're doing. But yeah, so relations. Does this kind of click in? The idea of just like, hey, you can take pairs of things, and if you got a bunch of pairs of stuff, this is effectively enough for you to define some new symbol you can put between two things. Cool. All right. Let's think of another one. Here, let's do another one. Here, let's do, because I think we get kind of stuck on the idea that everything has to be about numbers. Here's a relation. I'll even say from people in this class to hair color. It's the set of ordered pairs person color if person has color hair. There you go. That's a relation. Yeah? So for instance, you would have something like Bryce, comma, brownish, I don't know, in the set, all right? But you wouldn't have Bryce, comma, green in the set. Okay, does that make sense? You can do relations on anything. It doesn't have to be numbers. It could be sets of people. It could be weird sets. It doesn't have to be anything you've seen before. It could be literally any subset of a product. Cool. All right. Nice. So, fair enough. We've got all these nice relations. They're very general. I hope I've convinced you of that. You can just put anything you want in ordered pairs. No one's stopping you. What are they going to do? Call the cops? All right. But hey, relations can have many properties. Some ones we will consider. So we'll let A be a non-empty set, and I'll write a little tilde, be a relation on A. We say that tilde is, and now here's a bunch of different possibilities. You could have more than one of these, many of these. So you could say that this relation is, and does everyone get what I mean by like little squiggle is a relation? That is, what I mean is that in the same way we wrote like circle 5 between A and B to mean A squared plus B squared equals 25, you could take any relation and write like A little sim B to mean that AB belongs to the set R describing your relation. Maybe you would want to do something fancy and write something like sim with a little subscript, little tilde with a little subscript R, but that just feels like we're introducing too much notation. That is, every relation has some set of ordered pairs associated with it, and so just kind of intrinsically, you could, say, hey, I've got some set of ordered pairs, and I'll write a little squiggle between A's and B's if AB belongs to that relation. Cool? Okay. So I'm just using this as a shorthand so I don't have to write out the set of ordered pairs or anything like that. All right. Now, I'm doing this for just one set, a relation from a set to itself, which is pretty reasonable. We encounter those a whole lot. Here are a few properties. We'll say that this little squiggle is reflexive if A is related to A for all A in A. Okay. What's an example of a reflexive relation? Equal sign. Yeah, regular old equal sign. What about the less than or equal to sign? Yeah, that's also reflexive. What about the containment symbol from subsets? Reflexive, right? Many common relations you encounter are reflexive. What's a not reflexive relation?
Greater than or less than.
Yeah, just the greater than or less than sign. Right on. Perfect. Exactly. Very nice. By the way, think about this. What's the difference between the greater than and less than sign? I mean, we all know these things, right? But in terms of the relation, what happens? You just flip the order of the things in it. That is, every relation has this kind of opposite relation immediately defined, by just switching everything around. Yeah? So it's kind of nice. You could imagine that anytime you have a relationship, you could, for instance, turn this into B, and then, I don't know, if you wanted to keep the same convention, you could just draw here 5 backwards. And you could make, the same idea, but just, other way around. Flip the ordered pairs, right? Yeah? i.e. B, instead of sim this way, I'll go down and then up for my backwards one, if and only if BA is in my new R, I'll call it R op, contained in B cross A. That is, you can always make the opposite relation just by flipping the order of everything. Yeah? Oh, okay, cool. So you can just flip orders and you can make new things. All right, cool. reflexive relations in a set are those ones that when you flip the ordering and you create this opposite ordering, you just have the same exact thing. That is, a relation is reflexive if R op is equal to R, right? If you flip the order and it doesn't matter. Or actually, I said that backwards. This is, I'm getting ahead of myself right here. Something is reflexive if it contains the diagonal of AA. Oof, I got ahead of myself, yes. Symmetric, yes, we're a tiny bit ahead of ourselves there. Sorry about that. If it contains the diagonal, so all of the, thing and thing, same things, right? Then it's reflexive. There we go. Okay. Reflexive, good. Symmetric is the next one. So we say the relation is symmetric if A is similar to B, A is related to B, implies B is similar to A for all A and B in A. Okay, symmetric relations. Can you think of a symmetric relation?
Equal sign.
Equal sign, that's a great one. Yeah, right on. Okay. What's another kind of thing that might be, can you come up with one? Something,
An equation or right.
oh yeah, something like an equation like that. Okay, something, so not every single equation, but think about something like the circle. Yeah, totally. Yeah, if you can flip stuff, all right, right on. So,
Time sign?
a time sign. Oh. Okay, yeah, definitely. I see what you mean. Okay. So,
Or addition?
yeah, that makes sense.
Too basic.
No, that's not too basic at all. People are saying, so addition or multiplication, yeah, if you want to think of like addition as instead of producing a new number, just producing, I guess, like an ordered pair, and then we'll pretend the ordered pair is like a number, right? Like when you write 5 plus 8, right? You're kind of thinking of treating this as like 5 comma 8 and being like, well, let's make this be a new thing. And then if we just describe how addition works on the new thing or something like that, then 8 plus 5, well, that's the same thing. So that'd be like 8, 5, right? But yeah, okay, I see what you mean. That totally makes sense. Yeah. So if we wanted to like somehow describe addition in terms of creating ordered pairs and describing what that means, which is a very reasonable thing to do, we could do that. All right. That makes sense. Okay. Fun. So we could do that. There are other ones. We'll get to these pretty soon. Here's kind of like a well, we'll get to it. We'll get to some more symmetric ones and talk about why symmetry is nice. Here's another property. Anti-symmetric. If A is similar to B and B is similar to A, implies A is equal to B for every A and B in A. Okay, and then I'll write this last one up. Finally, we have transitive. If A is similar to B and B is similar to C, implies, getting really low on the board, sorry, A is similar to C for every A, B, and C in A. Okay, so basically the gist of it is just this. Antisymmetry, despite what its name may seem like it suggests, is not the opposite of symmetry. That would be asymmetry. Antisymmetry says that, hey, if A is similar to B and B is similar to A, then A is equal to B. That is, it says the only things that you can flip the stuff on are when they're the exact same. So could you have a antisymmetric relation that is not, say, reflexive? This is a good question. Think about it, maybe. So,
What's the difference between reflexive and antisymmetric?
reflexive says that A is similar to A for all A in A. Notice here, anti-symmetry says that if A is similar to B and B is similar to A, then A is equal to B, which would tell you that A is similar to A and A is similar to A, right? Yeah? But wait, be careful, this is an implication, right? You could have something where this is never true. There's never a case where this happens.
Still, A equals B.
So yeah, think about, for instance, the less than sign, right? Is A less than B and B less than A ever true for anything? Okay. So this statement is still true, though, isn't it? After all, if it was not true, you'd be able to show me a counterexample, right? There are no counterexamples, yeah? So it's true in a vacuous sense, right? Oh, interesting. Okay. So fun to think about. That is, it could be the case that you have an antisymmetric relation which is not reflexive. A great example of that is the less than sign, yeah? The less than sign is certainly not reflexive. 5 is not strictly less than 5, right? 2 is not strictly less than 2. In fact, nothing has this property, yeah? It is, perhaps you would say, irreflexive, which is another term people call relations, but we won't, bother to say that here. Though it's a perfectly reasonable thing to define. There's, in fact, an enormous laundry list of potential properties you can define for relations. We may talk about some more, but for now, let's get started with these 4, basically. So, okay, you could have something that's not reflexive, and in fact, specifically, never, ever is anything related to anything else, or to itself. But because of this, you could have antisymmetry. That is, it could be the case that this is never satisfied, this pair of conditions. And then it would vacuously be antisymmetric. Okay, fine. Cool. So there's a whole lot of different properties that relations can have. Let's think about it. Let's get some examples of these guys. Let's see what all this looks like. Example. Well, let's use the less than sign. So let less than denote the relation on R, Blackboard R, defined in the usual way. I.e., A less than B if and only if B minus A is positive. Okay. Then, this guy, this relation, is not reflexive. It is not symmetric. Is it? No, not symmetric, right? Since if you have, say, like 3 is less than 5, that certainly does not imply that 5 is less than 3, right? It's explicitly not symmetric. Maybe it's something like asymmetric, the opposite of symmetric. That is, having A less than B implies that B is not less than A. Yeah, implies not the statement here. That would be the idea of asymmetry. Asymmetry means that you can only have one, right? If a number is less than another number, then the second number is not less than the first one. Okay, cool. Is it antisymmetric? It is. It is antisymmetric, but only vacuously. I should think of how to spell vacuously. It is antisymmetric, but only vacuously, since A less than B and B less than A is never true. Yeah? So certainly, this could not be a false statement. When is an implication false? Remember, when is P implies Q false?
When P is true and Q is false.
When P is true and Q is false. So if P is never true, then we got a true statement. Okay, good. So the statement here, A is less than B and B is less than A, this is that statement here, where this thing implies that thing. Well, hey, you can never have this one be true and that one be false because this one can't be true, right? So you couldn't have that implication be false. All right, now what about transitive? It is transitive, right? 2 is less than 3 and 3 is less than 5, so 2 is less than 5, right? You can, follow a string of inequalities and then collapse the middle pieces. Does that make sense? All right, cool. So there's an example. What do you think of it? All right. So some relations seem reasonable. Some relations seem kind of weird. We can make up wild ones. We could make up nonsensical ones. We could make up any relation we want, just pairs of stuff. We can always take pairs of stuff. All right, some of them have nice properties. We've got reflexivity, symmetry, antisymmetry, transitivity. There are other properties you can have. You can have irreflexivity, which is just the exact opposite of reflexivity. You could have asymmetry, which is symmetry, but with the thing that is implied knotted out. You could have, some other kind of one, like for instance, do we want to have, say, for all x, there exists a y such that x is related to y? Or something like that. Do you want everything to appear somewhere in there? Maybe? Or you could perhaps say like, hey, if you, there are many other different properties, I guess is what I'm trying to say. Any sort of statement you can make about ordered pairs defines some sort of a property. There are tons of different ones that people talk about. If you go to, say, for instance, the Wikipedia page, relation, mathematics, you will see a very long list of properties people consider. There's tons of them. All right. And really all it comes down to is, hey, if you can make some sort of a predicate describing a predicate on an ordered pair, right? On ordered pairs, then bada boom, you've now got something good there, yeah? You've got a property of a relation. Okay, cool. Fun. You could even have a relation on relations. Think about that. Oh, weird. That's kind of fun. That is, there's nothing that stops A or B themselves from being sets of pairs. You can make relations on relations. You can stack it all as far as you want. And suddenly the simple concept of just taking pairs of things is a sufficiently nice building block that you can build some really crazy and complicated things out of it. For instance, what we will get to in a little bit here, what this is all leading towards is building the rational numbers in a reasonable way. Or we could even do something like build, say, like the integers from the naturals, right? After all, if you think about it, what's the difference between the natural numbers and the integers? Well, the natural numbers, you've got, well, I guess it depends on your convention. You either start at 1 or 0. But either way, there's like a kind of tiny trivial difference, basically. Like if you start at 0, then, well, hey, the integers are just 2 copies of the natural numbers, but one set of them has minuses in front of it, except that we take the -0 and the regular 0 to be the same thing, right? Otherwise, if you take the integers and you start the natural numbers at like 1, then the integers are legitimately 2 copies of the natural numbers. One of them has minus signs in front of them, and then you have to throw in some additional symbol called 0. But in either way, if you think about it, what's really the difference between putting something in, say, like the first or the second slot of an ordered pair versus drawing a minus sign in front of something, right? You could do that. You could describe, say, like a number n. You could make this into, this is not like an actual symbol, I'm just trying to describe like a way of encoding something like this. You could put n in the first slot and 0 in the second slot. You could describe minus n via putting 0 in the first spot and minus n in the second slot, right? Or sorry, putting n in the second slot. Oops, not minus n. And then you could only ever have to use, the positive integers, right? The naturals. And you could look at pairs of naturals to describe the integers. Now you would have to make up some nice rules for addition and stuff like that, where you would suddenly have maybe some more kind of issues, and you'd have to describe when things end up being the same. But hey, you could make something work like this, yeah? That is, then if you wanted to talk about like, you could say, oh, anytime you've got n, this is somehow the same as 0, 0, right? And then you would have created something that works like the integers just from looking at pairs of naturals. Yeah? Okay. Here's maybe an easier one to see than the example with the natural numbers and the integers. What about the rational numbers? For instance, what about 1 over 2 and 2 over 4? These are the same number, are they not? In fact, anytime you write a fraction a over b, it really is just an ordered pair, isn't it? There's something on top and something on the bottom. There's really no difference between putting it on top and bottom versus putting it in the first and the second slot, right? But somehow we have some sort of a special relation on pairs that makes these two things represent the same thing, right? We've made some kind of a relation on pairs that identifies these two things as the same. That is, we can write like an equal sign here, and we all know what that means. Like we say, okay, yeah, that's the same number. But really, if you think about, do you remember when you first learned fractions and you were like when people were like, what's 1 divided by 2? And when you were like a kid, you would say like 0.5. And now you say 1/2, right? But 1/2 is not, does it really feel like an answer, right? Like in some sense, like 0.5 is more correct or something, right? It feels more correct at least. At least when you try to teach kids this sort of stuff and you go like, oh, the answer is 1/2. And they say like, well, what's 1/2? And you're like, well, it's 1 divided by 2. That doesn't feel like what's the answer to 1 divided by 2 is, well, 1 divided by 2, right? That feels like that's kind of a bullshit answer, right? Okay, but underlying all of our, seeming reliance on the bullshit answer or something like that is this sort of property going on where really what we're saying is that what is 1 divided by 2? Well, it's any member of the class of fractions represented by 1 over 2, right? Any member of this set of ordered pairs that somehow we've all associated to the 1s over 2s, the 2s over 4s, the 8s over 16s, so on, right? All of them really represent the same thing. And so there's maybe actually something deeper going on when you say, what's 1 divided by 2? And someone says 1/2. What they really mean is somehow like, hey, what's 1 divided by 2? Well, it's a member of some sort of a class of equivalent representations of ratios of integers or something like that, yeah? Well, let's get to that. Let's formalize that. Let's figure out what the heck this all means. How are we building these things? There's all this stuff floating around in the background that we've not perhaps clearly described before. So let's try to describe a little bit of it. Here's the idea. Equivalence relations. This is the next business. I'll throw you an example. So, for x and y in the real numbers, define x is related to y if there is an integer n such that x minus y equals 2 pi n. Show that this relation is reflexive, symmetric, and transitive. So here is perhaps a good example of what's going on when we want to describe things as somehow being the same. What is this relationship telling us? It looks weird when I write it down, but if we stare at it for a minute, we're saying x is related to y if their difference is some multiple of 2 pi. Think about it like this. Here is an angle theta. Now if I go all the way around the circle and then back, there's another theta. I'll call these like theta 1 and theta 2. But look, I end up at exactly the same point on either one of them, right? It's like the same angle, right? Now, are they the same angle? In one sense, they are. In another sense, they aren't. In one sense, yes. Like if you went around that far, like, okay, you get to the same place there, right? If that's where you're placing like your, radial line or something like that. Okay, cool. In another sense, they're not because one of them span around once. Okay. But this is the relationship that says that, hey, when are two angles the same? Well, it's when they differ by some multiple of 2 pi, some multiple of complete rotations. That is, you could do yet another rotation. You could say, hey, what about this one where I go around once and then twice and then get back? That would be theta 3. Yeah? Same place. I end up at the same place, right? But now I have 2 pi, or 4 pi rotations additionally. Okay. So this is a good example of trying to say like, hey, when are things the same, right? That is, you can talk about, say, sines or cosines only looking at the interval from 0 to 2 pi, but you can also do it for more rotations than that just by using this relationship to collapse your angles back down to something in 0 to 2 pi. Yeah? Okay, kind of nice. So let's show that it's reflexive, symmetric, and transitive. So what about reflexivity? Since x minus x is equal to 2 pi times 0, x is similar to x for all x. Do you agree with that? That is, there are 0 additional full rotations. Yeah? Does that maybe make some sense? Feeling moderately okay? What about, say, symmetric? If x minus y is equal to 2 pi n for some n in the integers, then y minus x is equal to, well, that would be minus x minus y, which would be minus 2 pi n, which is 2 pi times minus n. Do you agree with that? Maybe? Sorry if I'm getting low on the board here. So, x related to y implies y is related to x for all x and y in the reals. Sorry, that's really low on the board there, and some people are not able to see past the monitor. All I'm pointing out is that, hey, look, if x minus y is 2 pi times some integer, then y minus x is 2 pi times negative that integer. Agree? Okay. What about transitivity? Let's try transitivity really quick. I'll do it right up here, since we're running out of space, and also people can't see the bottom of that board. Suppose x is related to y, and y is related to z. Then x minus y would be equal to 2 pi n for some n in the integers. And y minus z is equal to 2 pi m for some m in the integers. So, and here's where it's fun, we go x minus z. Would you agree that this is equal to x minus y plus y minus z? Add and subtract y? Yeah? Do you agree with that so far? Let's see. So I just added a y and I subtracted a y. I added 0. I changed nothing. Okay, but hey, look, x minus y, that's 2 pi n. And y minus z, that's 2 pi m. And this is just 2 pi n plus m. Do you agree with that? So, x is related to y, and y is related to z, implies x is related to z for all x, y, and z in the reals. That is, the relation is transitive. If I can go from one to the next, and from the next to a final one, then I can go from the first one to the final one. Cool. All right. Reflexive, symmetric, and transitive. Are these the same kind of properties that you see, for instance, in like the equals sign? Yeah? You're talking about numbers being equal to each other? Cool. Similarly, all of these properties seem to pop up. We'll see that reflexive, symmetric, and transitive relations are very important. In fact, they are what we will call equivalence relations. They enjoy all of the nice properties of the equal sign. And they let us define things like fractions in a meaningful way, which we will see next time. So, I'll see you next time with an exam to give back to you. Have a wonderful day.